Assalamualaikum warahmatullahi wabarakatuh. My name is Akila Siddiq from JC2 Al-Jazari, and today I will be explaining Kirchhoff's law and how to use them to solve circuit calculation problems. These laws are essential when a circuit is too complex for simple series or parallel formulas. By the end of this, you will see how they can help us to analyze circuits. Let's start with Kirchhoff's first law, which deals with electric current at the junction. It states the sum of currents entering a junction is equal to the sum of currents leaving the junction. This comes from conservation of charge. Charge cannot build up at one point. Everything that flows in must flow out. Take a look at the first diagram on this slide. Here, a wire splits into 2 points without branching. The current I1 flows straight through and continues as I2. Because there is no branch for current to split, so they are the same. That's why in here you can see I1 is equal I2. Now look at the second diagram. Here, I1 flows into a junction and splits into I2 and I3 that go off in different directions. All of the charge that comes in as I1 must leave through the two branches, so we write I1 equal to I2 plus I3. We will use this rule to write current equations whenever a circuit has multiple paths. Now that we know what happens at junctions, let's look at what happens around a complete loop in a circuit. It states that the total electromotive force or EMF in any closed loop of a circuit is equal to the sum of the potential differences across all the components in that loop. In other words, the energy supplied by the battery is completely used up by the components like resistors, lamps, or other devices in that loop. On the left side of the slide, you can see the circuit with two resistors, R1 and R2. The battery supplies is EMF, and the potential differences across the resistors are V1 and also V2. According to the law, we write sigma EMF equal to sigma V, and sigma V is equal to V1 plus V2. Or we can replace the voltages using Ohm's law. That's why we can also write sigma EMF equal to sigma current multiplied by resistors, which means current 1 multiplied by resistor 1 plus current 1 multiplied by resistor 2. Notice how I wrote current 1 for both resistors instead of current 2? That is because this is a series circuit, and in series, the current is the same. The same current flows through both resistors, so both voltage use the same current. This shows that when you go all the way around the loop, the energy provided by the battery is exactly equal to the energy used up by the components, so no energy is lost or created. This is another way of saying energy is conserved. This rule is very powerful for solving unknown currents or voltages in more complex circuits, especially when we combine it with Kirchhoff's first law. Now that we understand both of Kirchhoff's law and how they apply, let's put this into practice by working through a past paper question. We will use this rule step by step to calculate resistances, currents, and also power. State Kirchhoff's second law. Sum of EMF is equal to sum of PD around a loop. A battery of electromotive force EMF 5.6 V and internal resistance R is connected to two external resistors. The reading on the voltmeter is 4.8 V. Calculate the combined resistance of the two resistors connected in parallel. We know that parallel is 1 per R equal to 1 per R1 plus 1 per R2. And here the resistors are 90 and also 18. And if we calculate this on the calculator, it will be 1 over 15. R is equals to 15. We also have to calculate the current in the battery. We will use the formula of V equal to I times R. So I is equal to V per R. V is 4.8 and R is 15. So the current is going to be 0.32. Show that the internal resistance R is 2.5. We will use EMF formula, which is V plus IR. E is EMF, so 5.6 equals to, the V is 4.8 plus 0.32 times R. 5.6 minus 4.8 is 0.8, and we divide it by 0.32, so 2.5. Determine the ratio power dissipated by internal resistance R per total power produced by battery. We're going to use the formula of P equal to I square R. The current is 0.32 square and R is 2.5. (0.256). For the total power produced by battery, P is equal to IV. Current is 0.32 and V, the EMF is 5.6. 1.792. And then we divide it. 0.256 divided by 1.792. So the answer is 0.14. The battery in B is now connected to a battery of EMF 7.2 V and internal resistance 3.5. Determine the current in the circuit. We're going to use the second Kirchhoff law. Sigma EMF is equal to sigma phi. We know that sigma phi is equal to sigma IR. For the sigma EMF, we calculate 7.2 minus 5.6. And we know that we have 3.5 I plus 2.5 I. 7.2 minus 5.6 is equal to 1.6, and then it's going to be 6i. To divide it, and then we got 0.27.